So, how do you look for solutions under such problems? Under standard search formulation, we can start with a basic naive approach and then improve it. States are defined by the values assigned so far. So, we could have the initial state given by the empty assignment, and then a successor function like assign a value to an unassigned variable that does not conflict could be defined as a successor function, and the goal test could be if the current assignment is complete. Now, we should note that this is same for all CSPs. Every solution appears at depth n with n variables. Path is irrelevant, so can also use complete state formulation. And for a domain of size d, we have a branching factor b of n minus l into d at depth l. So, that leads to factorial n into d to the power n leaves, and this is a huge space to search. Could we do better than this? So, we can look for a spatialized version of depth first search. CSPs are solved by this, and the search is called backtracking search. The key intuition is that we build up to a solution by searching through the space of partial assignments. Order in which we assign the variables does not matter. Eventually, they all have to be assigned. If during the process of building up a solution, we falsify a constraint, we realize that this cannot be on the part of the solution. So, we can immediately reject all possible ways of extending the current partial assignment and backtrack. Backtracking search is the basic uninformed algorithm for solving constraint satisfaction problems. We look at one variable at a time. So, variable assignments are commutative, no fixed ordering is there, only need to consider assignments to a single variable at each step. And the second idea is to check for constraints as we go about. That is, we consider only values which do not conflict with the previous assignment. For that, we might have to do some computation to check the constraints, but then we get one step at a time towards the goal. Here is the backtracking search algorithm. The only thing I want to focus here or point you out is the idea of selecting the unassigned variable. We have a routine to select the unassigned variable. That is done in a way that no constraints are violated. Is used for a depth first search, values for one variable at a time, and backtracks when no legal values are left to be assigned. So, let us look at our 4 queens problem and try to understand backtracking search. So, here is the 4 cross 4 grid, and we start with placing our queen at this location. So, from the constraints that we have placed ourselves, that no 2 queens should attack each other, we know that this is not a legal position for the second queen, this is not a legal position for the second queen, but the third position on the second row is a legal position for the second queen. So, we put the second queen here and move one step further to look for a solution for the third row. This is no longer a legal position, this is not a legal position, this is no longer a legal position, neither is this a legal position. So, what we have realized at this point is that after we have assigned the second queen, we are not left with any legal position for the third queen. We have to backtrack. So, we remember what we started with, backtrack and get a new position for our second queen. With the new position for the second queen, we start once again with the third row to place our third queen. The first position is not legal because we have a queen here which will attack, but the second position is a legal position. Therefore, we move forward and look for the fourth row. So, we cannot have a queen here, neither we can have a queen here, nor a queen at the third position, nor at the fourth, on the fourth row. That means, after we have assigned this queen, we are not left with any legal positions in the next step. So, we have to abandon this path and backtrack. So, we backtrack, and now where do we backtrack? We need to understand that we have already looked at all possibilities for the second queen given the first queen. So, we must backtrack to starting with another position for the first queen. So, we backtrack to a point where we put our first queen on the second column, then we have the queen here, the third row we could have a legal position at this. Given these three queens, we could get a legal position for our fourth queen. So, that is our solution. So, that is how backtracking search works. Let me repeat this very quickly one more time. So, we had some legal positions up to this level, and when we tried for the third level, we could not have a legal position. So, we backtracked and started with an alternative in the second position. We could have a third position very nicely, but we could not have a fourth position placed. But then we have realized that we have exhausted all possibilities of our first queen itself, and therefore backtrack to removing our first queen to a different position, and once we had done this, we could arrive at a solution. So, plain backtracking, as you have realized, is an uninformed algorithm. We do not expect it to be very effective for large problems. We remedied the poor performance of uninformed search algorithms in our previous discussion of state space search by supplying them with domain specific heuristic functions derived from our knowledge of the problem. But because constraint satisfaction problems have in themselves some structure or representation, we can solve CSPs efficiently without such domain specific knowledge. General purpose methods that address the following questions improve backtracking search. A. Which variables should be assigned next, and in what order should these variables be tried? B. What are the implications of the current variable assignment for the other unassigned variables? C. When a path fails, a state is reached in which a variable has no legal values, can the search avoid repeating this failure in the subsequent paths? General purpose methods can give huge gains in speed and in improvement of backtracking search. Ordering which variable should be assigned next, in what order should its values be tried, or filtering, can we detect inevitable failures early, or structure, can we take advantage of the problem structure. These can lead to improving backtracking search.